Go casual conversational cartoon curriculum, very concise and relatively correct, as simple as possible, as soon as possible. Anatomy and Physiology is chapter 18, and here we are again, and we did a brief little thing about where hematopoiesis occurs and about the breakdown of red blood cells. Now we need to say a little bit more, and a little bit more comes down to this issue. Let's say you took a sample of blood, and in the sample of blood, you centrifuge the thing, and you got your plasma, your buffy layer, and your hematocrit. Here are some terms that represent the relative thickness of these things and what it might imply. If for some reason the buffy layer is a little thicker than normal, normally it's less than 1%, that could represent leukocytosis, which means you have a higher than normal number of white blood cells. That might imply some kind of infection. Of course, knowing what kind of white blood cells there are might tell you what kind of infection it might be. If it's smaller than normal, that might represent leukopenia. And leukopenia refers to less than the normal number of white blood cells. So this one right here, you have a lot of security forces in your blood circulating around. Down here, you don't. Each one represents a unique problem. If we were looking at the hematocrit and we noticed the hematocrit was above 45%, maybe up towards 50%, that might represent polycythemia. The word, of course, poly means many, cyte means cell, emia refers to blood condition, and in this case, you have a higher than normal number of red blood cells. Now, there are natural forms of polycythemia. For example, being hypoxic might prompt you to produce more EPO and might give you sort of a reactionary polycythemia. There's kind of an athletic version of this too. As you exercise more, as you give yourself more hypoxia, you'll make more red blood cells and you might actually produce more red blood cells, resulting in polycythemia, which of course would give you, in essence, more oxygen carrying capacity and a bit more endurance, something you might want to do. If for some reason you have less than the normal number of red blood cells, if you had a lower hematocrit, lower than 45, that might represent anemia. Emia means blood condition, and A refers to not. It's as if you don't have blood. Two possible reasons for this. One could be you don't have enough red blood cells, and there's three general versions here. There's hemorrhagic anemia, hemolytic anemia, and aplastic anemia. With hemorrhagic anemia, you're bleeding, you're losing your red blood cells, so the number's down. And hemolytic, for some reason, the red blood cells are being destroyed. Malaria is a good example of this. And in aplastic anemia, for some reason, the red blood cells aren't being made, or their form is bad, and so they're not functional. So, one form of anemia could be a low hematocrit as a clue, and not having enough red blood cells as the reason. But it is possible to have a normal hematocrit level, but still be anemic. The anemia basically refers to the fact that the blood isn't doing its job as it normally does, as if it's not there. Well, you could have a normal number of red blood cells, but still have anemia. And this might be a reason, because you don't have enough good hemoglobin inside those existing red blood cells. Here's three possible ideas, simple ideas. It could be due to iron deficiency. For some reason, you don't have enough iron inside your diet, therefore you can't supply the iron to the hemes inside the hemoglobin molecules, and the red blood cells, even though they're there, can't carry the oxygen as well as they should. Pernicious anemia. This is due to a lack of vitamin B12 in your diet, or the inability to absorb B12, which sometimes is due to a stomach problem. Anyway, with pernicious anemia, you have red blood cells that are rather pale and sometimes kind of large, and pernicious refers to that, that they're not doing their job, they're pale, they're just not a good representation. Sickle cell anemia. This is a genetic disorder in which the cells lose their biconcave disc shape in hypoxic situations. They collapse and become somewhat sickle shaped. Now, in the biconcave disc shape, they can bounce off walls, they can go through junctions where arteries are bifurcating and there's no snagging and dragging, not like inner tubes going down the rapids. However, with sickle cell, the cells lose that biconcave disc shape. They do form a bit of a sickle, a hook, and they can snag and drag and pile up and eventually plug up things creating occlusions of all kinds. Okay, real quickly here, hemostasis. Hemostasis is something that deserves a lot of attention. This is just an overview. Hemostasis refers to constant blood condition, and it's basically saying that red blood cells have to be inside blood vessels to be effective. Therefore, you got to make sure the blood vessels don't have any holes in them. If there's any kind of damage to a to a blood vessel, here are the three general steps for repairing it. Three general steps for hemostasis. First is vascular spasm. Chemicals released due to broken cells, either outside or inside the blood vessel, can stimulate smooth muscle inside the wall of the blood vessel to constrict. When the smooth muscle constricts, again it's wrapped around the lumen, it causes the lumen to become more narrow. This slows down the blood flow in that particular region, and so therefore you're not flushing the area out as readily as you were. Likewise, the formed elements coming through the blood are not acting like sandpaper, scraping things off the side. The next step is platelet plug formation. In this situation right here, chemicals that were released at the damaged sites stimulate thrombocytes, platelets, circulating through that area to enlarge, form sort of finger-like projections like pseudopods, and become sticky. They pile up where the chemical comes from, which is at the damaged site. And so you now have a plug, a pile of platelets right there over the damaged site, thus creating a temporary patch for that hole or that damage. The next step is coagulation. In coagulation, there's a cascade of chemical reactions, here grossly oversimplified, that tries to create fibrin, which can then help to ensnare in a sticky web formed elements moving through the area and create a patch, create a clot over the platelet plug. Story goes like this. If the damage is found inside the blood vessel, it's called an intrinsic pathway. If it comes from the outer part of the blood vessel, it's extrinsic. There's approximately 13 factors that are involved in here, and they're represented by Roman numerals I all the way to XIII. And they come from these two different directions. Now, also along the way right here, vitamin K and calcium are absolutely significant in this being successful. So we can't forget the significance of vitamin K to blood clotting, nor calcium to blood clotting. Whatever the pathway is, short or straight, it leads to the formation of something called a prothrombin activator. This particular chemical will cause prothrombin, a dissolved plasma protein, to convert to thrombin. Now remember, prothrombin was made inside your liver. So this prothrombin activator changes prothrombin into thrombin. The thrombin then interacts with fibrinogen, another plasma protein dissolved in the plasma produced by the liver, and it causes this fibrinogen, which was dissolved, to polymerize, and sticky subparticles cling to each other and form threads. These sticky threads are called fibrin. The fibrin forms over the site of the damage, over the platelet plug. It tends to catch red blood cells, white blood cells, and other platelets in its web. Then once you get this pile of fibrin and captured formed elements, the fibrin will contract. That's called retraction. And when it contracts, it squeezes down on the pile of formed elements. It squeezes serum out of the pile, and it's now put the patch closer to the surface and opened up the lumen of the blood vessel in a way. Okay. Later on, after the damage has been repaired in the wall of the blood vessel, it's important to get rid of that patch, and retraction created the low patch, and fibrolysis will actually destroy the patch, hopefully slowly, so the chunks that come away from the thing won't create emboli or other problems downstream. 3 words right here before we lose our time here, and that is margination, diapedesis, and chemotaxis. If this represents a white blood cells can circulate through the blood, but they also have the ability to pull to the side of the road, so to speak. That's called margination. Move through the wall of the blood vessel, particularly if it's a capillary or a venule. That process is called diapedesis, which means a cross-step process. So they're stepping across the wall of that blood vessel. Then they seek out a target, and they do it by going from a low concentration of a chemical to a high concentration of a chemical. Now that chemical may be something being released by a damaged cell, or perhaps by a pathogenic cell, or perhaps it was a mast cell that dumped something like histamine and is trying to attract attention. Whatever the situation is, the chemotaxis is how the white blood cell finds the source, which is probably where the action is going on. Remember, white blood cells are blind and deaf. The only way they know where they're going is by a sense of smell, taste, if you want to say that, because they know there's chemicals in the environment, and also when they bump into something, by a sense of touch, because they can evaluate the molecules found on what might be a potential target. Down here, ever so fast, this thing right here just reminds you of what you already know, and that is, if this is the circulatory system moving around from the lungs over here to the hard-working cells over there, again, grossly schematically simplified, over here in the lungs is where you pick up the oxygen, put it on the hemoglobin right here. At least 98% of the oxygen is being carried by the hemoglobin. That process is called loading, and what's being created is oxyhemoglobin. So over here in the lungs is where you load the oxygen, where you form the oxyhemoglobin. The blood circulates over towards the hard-working cells, and next to the hard-working cells, where the oxygen level is low, and the pH is low too, the oxyhemoglobin will fall apart and release the O2 so it can diffuse over to the cells where the level is low because they're using it up. That process is called unloading, or it's oxyhemoglobin dissociation. The hemoglobin is still part of a story here because after it drops off its oxygen, it's like a cab without a fare, and cabs don't like that. Hemoglobin doesn't like that either, and so therefore the hemoglobin can combine with a carbon dioxide molecule. Approximately 20% of the carbon dioxide, 20 to 23% of the carbon dioxide that's moving through the circulatory system is being carried by hemoglobin, and that's called loading, and that's called carbamine hemoglobin formation, making that thing right there. That is returned back to the heart, pushed into the pulmonary veins, pulmonary arteries, and in the pulmonary arteries, the carbamine hemoglobin will fall apart. It'll dissociate, and it'll unload the carbon dioxide. The carbon dioxide will then go from greater concentration inside the blood to lesser concentration inside the air of the alveoli.